If you were here last week or listened online, we had a really neat discussion of structural equation modeling by Ryan Poet from the University of Delaware. So today is really kind of a follow-up on that with another aspect of structural equation modeling. Pradyush Sharma is our speaker today. He's in the College of Business and Economics at University of Delaware and in information systems. And so he's going to present an aspect of structural equation modeling, partial squares that can be used for exploratory data analysis. Thank you.
Should I be standing here?
We can't see you online unless you're near the podium.
Okay, so I have to be here somewhere. All right. Good afternoon. My name is Pradyush Sharma. My first name is a little bit difficult to pronounce, but it makes sense in India, but oh well. The last name is far easier to pronounce, Sharma, and I am an assistant professor at the Lerner College of Business and Economics at the University of Delaware. I have a bachelor's and graduate degree in computer science, and my PhD was from Pitt in information systems. I do not really have a statistical background. In fact, the first ever statistics class that I took was in the second year of my PhD program, and it was Ryan and my common advisor, his class, and that was the ANOVA class that I took. But I kept taking the classes, and one of the things that I got really interested in was the partial least squares structural equation modeling. I come from the information systems discipline and PLS, and when you have that much quantity of data, sometimes it just gets overwhelming to figure out what to do with it. Sometimes you don't know what are the right questions to ask. Sometimes you don't know how to ask them. Sometimes you don't know the right methodology to choose. And sometimes you don't really have theoretical background. The theories are not developed enough in certain fields that you could create hypotheses for them. So when you have a situation like that, predictive analytics comes into play. And so today's talk, I'm going to try talking about how you can use PLS, structural equation modeling, for that. There are other techniques that you can use for predictive analytics. You can use regression. All kinds of regression can be used for that. There is neural networks. People have tended to use neural networks for that. And there are a lot of other machine learning techniques that people have used for prediction. But none of these techniques have been so far with what we call the latent variables. So latent variables are variables that you don't really observe right away. Instead, these are more kind of abstract concepts. So for example, one of the abstract concepts that I'm going to talk about today is trust. You can't really measure trust because there is no scale for it, right? It's not like blood pressure, it's not like heart rate. It's a concept that we human beings use in our day-to-day language. We know what it is, we instinctively know what it is. You can even define it. And typically the way to measure trust is through survey questions or some other items that you might have that you hope are tapping into this latent higher end construct. So PLS is really, really useful for dealing with latent variables. So in this talk, I'm going to try differentiating between explanations and predictions. And the first question that you have to ask is, are they same? And John Searle said, predictions and explanations are exactly symmetrical. Explanations are predictions about what has happened in the past. So you're looking retrospectively you have data, things have already happened in the past, and you're trying to create explanations for them. And predictions are explanations about what's going to happen. So something that hasn't happened yet, and you want explanation for that. So in that sense, they are very symmetrical. But how we go about doing predictive analytics and explanatory modeling, there are differences in that. So the agenda for the talk today is differences between explanatory and predictive modeling. Briefly compare SEM, which Ryan talked about earlier, to PLS-SEM, looking at the strengths and weaknesses of both these techniques. And then I'm going to present an example comparing the models on their explanatory and predictive abilities in the e-government citizen trust context. So all of you must have heard about the Obamacare website fiasco, right? So the website went on, the healthcare.gov website went live, and there were tons of problems with it. And as a result, President Obama's ratings suffered. Okay, there were a lot of problems, a lot of issues, just because of that website. So think about this. Creating a good website was that important for the president. Okay, so we are going to talk about the study that we are recently doing in that context. So before I begin, let me quickly ask you a question. What do you, I know there's a lot of statisticians here and a lot of practitioners as well, and I want to keep the talk very accessible to all of us. As I said, I'm not a statistician, I'm a practitioner. What do you understand when I say explanatory modeling as compared to predictive modeling? What's the general sense that you have? Anybody want to take a shot?
Well, I mean, in explanatory, you look at variables that you know already, and you try to figure out what's the impact of one specific variable that you are interested in on some outcome.
Right.
A predictive modeling, at least for me, is that you don't know which variables will have impact on the outcome, and you are trying to figure out which variables in the future will have impact on the outcome.
So this is a very good point. She says in explanatory modeling, you generally have a sense of which variables to include in your analysis, and you have a general sense of how they impact the dependent variable of your interest. In predictive modeling, that's kind of an open-end thing. You don't really know which variables to include. You don't really have the theoretical base to say, okay, this variable affects the dependent variable that way or whatever. So you're more in the exploratory kind of mode. So that is a big difference between the two techniques. Let me give you a quick example from physics. In the early 1900s, people kind of discovered that the orbits of Mercury had a slight deviation from what the Newtonian laws of gravity were predicting. So Newton's laws were really, really good at predicting and explaining the orbit of Earth, Mars, and all the other planets. And Mercury was standing out. There was a glitch in its orbit. And no matter how you tried, astronomers couldn't figure out why that glitch in the orbit existed based on Newtonian mechanics. So here comes Albert Einstein with his theory, and Albert Einstein's theory actually explained why there should be a glitch in the orbit of Mercury, why it should behave a little bit erratically than other planets. So here's a case where we had a theory which was a very well-established theory, Newton's theory, but it couldn't explain a certain phenomenon that we were already observing. And so here comes a new theory which tries to explain it and does a good job of it. Not only that, Einstein's theory actually predicted certain other phenomena that were really, really mind-boggling. So for example, it predicted if you go fast and fast enough, there's going to be a shrinkage in space and time. So if you're an astronaut, if you're going around the Earth in circles at really, really high speed, time slows down for you. Now that's a prediction, and that's a remarkable prediction that his theory was able to make. And for the next 50, 60 years or so, nobody could actually, ask this question whether this prediction is good or not. So 60, 70 years later, when astronauts started going up in the orbit, they found out, yes, Einstein's theory was actually correct. So he had predicted something. And when you have a solid prediction behind the theory takes a life of its own. Explanations are good because they make sense for mere mortals like you and me. We explain things. But when your theory is able to make certain predictions which we don't really have any idea about, then the theory takes quality to a next level. And that's why a lot of people really, really rate Einstein's theory of relativity so highly, because it's making predictions that nobody ever thought about. So, I'm going to try really quickly to distinguish between explanatory and predictive modeling. What are the goals of them? What is the focus? What is the role of theory? I know there's a lot of information here, but I'm going to quickly talk about these things, and just so that you guys have a sense of what is the difference between explanatory modeling and predictive modeling and how PLS fits into the picture. So for explanatory modeling, the real goal is theory testing. You create models based on theory. You have hypotheses. Each of these paths represent hypotheses, and you're really testing whether these paths differ from zero or not. Are they significantly different from zero or not? So you're really looking at causal relationships between theoretical constructs. Okay? And it's very heavily theory-driven. Predictive modeling, on the other hand, is really looking at predicting new phenomena. Or, in empirical modeling sense, you're trying to predict unseen data. And when I say unseen data, I mean data that your model has not seen. Okay? And predictive modeling is really, really based off of associations between measured variables, and it's very data-driven. So in many cases, it even comes across as atheoretical, meaning that the role of theory is reduced. Okay? So the role of theory is very critical in explanatory modeling because you're trying to explain something. Predictive modeling, less so. You really don't care so much about theory as long as you have good sense of which variables to include in your analysis, but you're really in a very prospective kind of mode. Okay? And the goal is to test the accuracy of your predictions. You really want to build a model that is giving you good predictions, and how good of a prediction that is. Okay? So, related to that is the role of statistical significance in explanatory modeling, as Ryan must have presented to you. The statistical significance takes a critical role in explanatory modeling. You really are interested in path estimates and whether those path estimates are significantly different from zero or not. In predictive modeling, it is irrelevant. You don't care about whether a given path is significantly different from zero or not. You don't care about it. All you care about is making good predictions. And sometimes actually deleting certain significant paths have been shown to increase the predictive accuracy as well, if the effects are weaker. So the risk, yes, question.
But in practice, a lot of people use the statistical significance of predictive models to decide which ones to include.
Yes, absolutely. So,
which is not really the best idea.
Yeah. So in practice, I think that this is coming from the paradigms that we have grown accustomed to. We are very comfortable with the hypothesis testing paradigm, and we kind of want to stick with it. And so the practice of predictive modeling kind of gets muddled with that practice. The risk type, what kind of risks you have in explanatory modeling, you're really looking at type 1 and type 2 errors. You don't really want to make any false positives, neither do you want to have any false negatives, right? In predictive modeling, on the other hand, the greatest risk is overfitting, the lack of generalizability. Okay, so overfit models predict poorly. I will talk about what I mean by overfitting. So if you don't know what overfitting is, I will talk about it very briefly in the next slide. In terms of model evaluation, explanatory modeling, you're really looking at fit statistics. So R squared is one measure. It's just the explanation of variance, how much variance has been explained in your data, or the other fit indices from SEM, such as RMC and CFI. Okay. In predictive modeling, you're really looking only at the accuracy of model in making out-of-sample predictions. So you're looking at mean errors and root mean squared errors. So the metrics differ between these two techniques. In terms of competing models, explanatory modeling, generally you would have one monolithic model, and you would either confirm the structure or you would disconfirm the structure. So you create a model based off of theory, and you either you confirm that the structure or you disconfirm. Okay. So there's really a much reduced scope of competing models. But in predictive modeling, competing models are fair game because you don't care so much about the structure of your model. You just go and work with whatever structure comes out tops, and that's the structure that you would go with. The final thing that is a very crucial difference between the two techniques is the samples required for analysis. Generally, in explanatory modeling, you have one sample, and you take the whole sample for model building and fitting the model and so on. In predictive modeling, you would typically split the sample into two. The first sample would be called the training sample. The second sample would be called the holdout sample. So right off the bat, you can see that if you want sizable training and sizable holdout samples, what are the two most commonly used structural equation modeling techniques that are out there with latent variables? And so how do they compare? And so this is the table. It talks about the basic comparison between these techniques. The modeling goal is very different in structural equation modeling and PLS. The modeling goal in structural equation modeling is really testing the causal hypothesis, very theory-driven. The focus is on minimizing the difference between model-implied and observed covariance matrices. Okay? On the other hand, PLS, the goal is exploratory modeling, predictive modeling, and you're really interested in maximizing explained variance, R squared. Okay? You can have path significance testing in both these techniques, PLS and ML-SEM, both allow you to do the path significance testing. ML has a global optimization function, meaning you can compare the two nested models and say one of them is significantly better than the other or not. PLS doesn't allow you to do that. In PLS, all you're given is the R squared value, and if you're running two models, the only thing you could say is one of the models has a higher R squared than the other one. That's about it. There's no global optimization function in PLS. Although there's a paper coming out very soon, or it might have already been accepted, that does allow you to do that as well. Okay, so you should be able to say one model is significantly better than the other or not. The estimation method that is used is maximum likelihood. Generally, there are other estimation methods out there. PLS uses the partial least squares, and the big problem with maximum likelihood is that it requires normality of the data. So that is a major assumption in ML-SEM. In PLS, there is no assumption of the data as far as the normality are concerned. So it's in that sense, it's very flexible. And I have done some simulations, and researchers in other fields have also done simulations where they've tried to vary data distributions, and it seems that PLS is generally robust against different kinds of violations to the data. Model evaluation, you must have seen in Ryan's class, ML-SEM has chi-squared, RMCA, CFI. These are the indices there. In PLS, you're really looking at R squared, adjusted R squared. Those are the two most commonly used indices. And one of the major problems with R squared is overfitting, or the threat of overfitting. That you could actually put in more and more variables, your R squared would keep on increasing, but the problem with that approach is that your predictive accuracy will go worse and worse. So for that, what you can do is there are some information criteria that you could use, and this is to answer your question. So information criteria like the Akaike index or the Bayesian information criteria, and I use these in the study, and what they try to do is that they try to balance R squared with the model complexity. So they guard against overfitting the model. In terms of convergence rates, SEM has inferior convergence rates, meaning that sometimes the algorithm just wouldn't give you results. It wouldn't do anything. So PLS generally tends to converge. It has superior convergence rates. In terms of parameter accuracy, if you're only interested in the path estimates and the accuracy of the path estimates, SEM is superior. PLS is inferior for structural paths. But for measurement model paths, we'll talk about that, but for measurement model paths, PLS is okay. Predictive accuracy, PLS is far better. And I've listed some of the software down there below. If you haven't used PLS, Smart PLS is the most widely used software, and you can also use the R package if you don't really want to spend a lot of money, but you would have to do some coding yourself. So how does a PLS analysis proceed? I gave a lot of information up front, but I really want to show you how a PLS model looks like. So this is a hypothetical example. This is a snapshot from Smart PLS. And here, what I've done is you have product quality, the one on top. So I have product quality. This is product quality, and this is the perceived value. So I've taken survey of customers. Let's just say they're from Walmart. I've taken their survey. I've collected some of these items. These are the survey questions, and each of these questions load up on certain constructs. So product quality, because it's a latent construct, you would measure product quality based on 2 or 3 survey items, and those are loading up here. The other thing that is here is a perceived value. So what is the perceived value of the product that I'm buying? So there are some questions related to that, and both of these feed into customer satisfaction. If you have higher product quality, higher perceived value, then a customer is satisfied, and then that leads to the loyalty. So that could be one simple PLS-based model. Now, as you'll notice, there are two kind of parts to the PLS model. The first part, with the yellow boxes and the arrows going towards them, is the measurement model. Okay, this is the measurement model because you're really measuring the construct. These models that are between the blue ovals are the structural model. This is where you'll typically do the path testing, the significant path testing. Okay? You would create hypotheses based on these. And so the way the PLS analysis typically proceeds is that the first thing that you would establish is the measurement model adequacy. So if the measurement model is good, meaning your survey items are good, they're loading up on the right constructs in the right way, you have convergent validity, discriminant validity, construct validity, then you can proceed to looking at the structural paths. So that is the second step in PLS analysis. So let me just quickly go down and show you the 2 stages in a general PLS analysis. This is not doing any prediction right now. These 2 paths have nothing to do with prediction at this point. This is just establishing a measurement model adequacy. You're looking at the item loadings, the validity, and then you move on to the structural model adequacy. Here you're looking at the path coefficients, you're looking at R squared, adjusted R squared, and typically the focus is what is the R squared in the dependent variables, so customer satisfaction and loyalty. You really want to say, okay, these 2 constructs explain 50% of variance or 60% of variance in satisfaction or loyalty. The more you explain, the better it is in terms of explanation. Okay? Your model is doing better in terms of explanation. Now, when I want to use PLS for out-of-sample prediction, these are some of the additional steps that I would have to take. And what I do is first I create the training and holdout sample sets. I would run the model on the training data. I would get the model coefficients from the training data, use those model coefficients and the holdout data to create a predicted value of the dependent variable. So I would create the predicted value of customer loyalty. That's what your model is predicting. The next step, what you would do is that you would take the actual observed value of customer loyalty, and based off the predicted value and the actual observed value, then you can calculate the distance between them. And that distance becomes your predictive accuracy. Okay? And so typically what you would use is root mean squared error. That's the formula. So here what you're doing is for all the n values in the holdout sample, you would just subtract the predicted value from the observed value, square it, and divide them by n. That's the formula. Mean absolute percentage error, that's just giving you the percentage error. It's a very similar metric also. Observed minus predicted divided by observed, and you just take the modulus of those. So these are typically used in out-of-sample prediction. You might see these metrics being used in forecasting also. So if you're into the forecasting literature, you might see these values, metrics. So now, given this background, I want to move on to show you an example of how PLS could be used. And so the paper that I'm going to present here, and I'm not going to present a lot of detail on it because of the time. In which model do we trust and when? The reason that I have the study which says in which model do we trust and when is because in the e-government trust literature, there are typically two models that researchers have used. The first is the expectancy disconfirmation model. So overall expectations that a customer has going in, how it affects the overall quality, and if those expectations and the quality perceptions, if they are disconfirmed or not disconfirmed, positively confirmed or negatively confirmed, that leads to satisfaction, and then satisfaction in turn is supposed to lead to trust. That's one theoretical model that has been used. The other theoretical model that is typically used is the service quality model. The service quality model is all about the actual service itself. So as you go on to the Obamacare website, let's say, you look at the information quality. You have a sense of efficiency of service. You have a sense of the website quality. That creates the perception of the overall quality, and that is supposed to lead to satisfaction and trust. So this is another model that has been used in literature. The question that I'm going to ask here in this study, which of these two theories is better for explanation, and which of these two theories is better for prediction? And once I've established that, I want to know what are the boundaries of applicability of the best model. In other words, where can the best model be applied and where can it not? Where does it work stronger? Where does it work weaker? Okay? So that is the question that this study asks. So quickly going through the steps in model comparison, I would create competing models. So based off of those two theoretical models, I would create alternative model specifications. I would split the data into training and holdout samples, and then I would go ahead and compare the models for their explanatory power. I would look at their parsimony. I don't want overfit models. I would look at cross-validation, which is in-sample prediction. This is another metric that is that PLS provides. And then I would look at out-of-sample prediction using holdout sample. Okay? And finally, I would look at the boundary conditions. So given these two models, the expectancy disconfirmation model and the service quality model, I would first create the alternative models. Okay? So this is the alternative models for expectancy disconfirmation theory. What I did was, since we had 3 constructs, or let me go. Yes, so 4 constructs, and satisfaction always predicts trust. So for three other constructs, I would take all possible subsets. So I'm going to create all different paths, all combinations of different paths. Okay. So this is where I'm going a little bit off theory, a little bit atheoretical in the sense that I'm just trying out all the different structures possible. Okay. So each of these check marks actually presents which path was included in which model. So I created 8 models. The 1x model only has the satisfaction predicting trust, and that's the original model. And if you look at the 8x model, it has all the different constructs predicting trust, so expectations, quality, disconfirmation, satisfaction. So this is the saturated model. I would do the same thing for the service quality model. Now, since service quality model has 4 additional constructs in addition to satisfaction, I would get more number of models. So I have 16 different models. So in essence, what I'm doing is I have these bunch of 24 different models, different structures, if you will, and I'm going to put them into a race. And I'm going to say, which of these structures works best for explanation? Which of these structures work best for prediction of trust? And that is the question that I'm going to ask. So this looks very, very threatening, I know, but it's in reality, it's a very simple table to follow. What I've done here is that I have ranked all these 24 models. So you can see the overall rank here. I have ranked all these models first based on the explanation power, which is the R squared, adjusted R squared, and goodness of fit. Parsimony, which is all these indices. So these are all the information theoretic criteria, AIC, BIC, and all the related criteria. And Q squared is the in-sample prediction. So what I've done is for all these 24 models, I've created these values. And based off of these values, I want to know which model comes out the top. The model with the highest R squared, the model with the highest adjusted R squared is ranked first by that criteria. AIC, if you look at the information theoretic criteria, the model that comes out on top has the lowest value. So the lowest value on AIC or BIC means that model is preferred model over the others. So if you look at the AICC value here, that value is -11. That is the lowest value across the board. That means AICC ranks this model first. And I do the same for all the other criteria. So I just calculate the rank of models based off of each of these criteria. And then I just add the rank totals and arrange them in increasing order. That means that this model comes out tops in terms of all these criteria taken together. If I took a vote of all these criteria taken together, that model was the topmost model. Okay. Yes?
So this model comparison just for the structural models also include the measurement models?
So that's a very good question. Is this comparison only for the structural part or the measurement part? So in PLS, what you would do, you would establish the measurement model adequacy, and then the focus shifts entirely on the structural part. So I'm assuming, and I've done the analysis, I'm not showing you the results, but I'm assuming here that the structural model, sorry, the measurement model was adequate. Once the measurement model was adequate, then I move on to the structural.
This is a very big, strong assumption.
No, I did the testing. I'm not, for the presentation, I'm not showing you the results, but I did the testing. So when I did the testing, the measurement model is adequate for all the models. Okay? Now, if you're looking at the models one thing that you might see here, and I've circled them in red and green if you could see. Can somebody tell me what's going on there? If you look at the top quarter of models, top 1/4 meaning the top 6 models.
Half of them are from the explanation.
Half of them are for the expectancy disconfirmation, and the other half are the service quality model. What's more, they neatly come out in different clusters, in the sense that the models that are coming off of expectancy disconfirmation theory are always ranked higher when I look at explanation, parsimony, and in-sample prediction. But when I look at the service quality models, they're good, but they are not ranked as high as the models from expectancy disconfirmation model. Okay. Now, what I would do is I would take the top quarter of these models, the 25% top models, and I would put them into a race for out-of-sample prediction. So here, I've taken the top 6 models from the previous slide and put them into a race for out-of-sample prediction. And here you can see this model has the lower value on RMSE and MAPE is better, and higher value on out-of-sample R-squared is better. So if you look at this 2.31, that's consistently the lowest value. So that's this model is ranked first by RMSE, meaning that this model has the lowest error in prediction, best model for prediction. The same here, and it has the out-of-sample R-squared of 34%, meaning it's able to explain 34% of the unseen construct. So when I rank the models like that, a different story emerges. The service quality models are on top, and the expectancy disconfirmation models are down below. It's a complete reversal. The models from expectancy disconfirmation model that were really, really good at explanation are not that good at prediction. On the other hand, the service quality model, which wasn't doing as well, is now really, really better at prediction. Okay? So, let me show you what these models are. So, the topmost model for prediction is 13 served, and the topmost model for expectancy disconfirmation is the 8x model. And so I want to show you the structure of those models. This is the 8x model. It's best at explaining trust. And the red lines that I have here, these are just the paths that I added in addition to the original model. So the original model is the black paths. The red paths are the ones that I added later. So this model seems to do the best in terms of explanation, parsimony, and in-sample prediction. But when I look at prediction, out-of-sample prediction, 13 served does it the best. Again, the black lines are the original model, and the red lines are the additional lines when I created the alternate model specifications. So this model is really, really good at prediction also. Now the question is there a good compromise? Is there a model that does good for explanation as well as prediction? Yes, 13 served does that, because if you go back and look at the R-squared values here, the R-squared value for 13 served is 64%, and the expectancy is 65.7%. So that is just a difference of 1.5 percentage points when it comes to the difference in R-squared values. And for all the practical purposes, I would say that these R-squared values are fairly similar, in the same ballpark. They're not extremely different from each other. But if you look at the out-of-sample R-squared value for out-of-sample prediction, this value, 34%, compared to that value, there's a big gap. Right? 34 and 21. So I would say the 13 served gives you the best mix of explanation power and prediction power. Okay? So now I've established what that structure is. I would go ahead. Oh, this way. And try to move on to the next slide. So what is the moral of the story? Best fitting models may not be the best predictive model. Okay. Best fitting model was 8EXP, but it wasn't as good for prediction. Okay. So when you're making this judgment, when you're doing any studies, keep that in mind. Please keep that in mind, that when you're creating a model that fits the data really, really well, it doesn't mean that it's going to be the model that is going to do best for prediction. So if your goal is prediction, your model might turn out to be completely different than. Now what I do is, in order to test the 13-serve model, and I want to look at the boundary conditions. Where is it applicable more than others? And so what I did was, I tested for significant path differences for age. So I lumped together generation X and Y respondents and baby boomers. I have tested them for political identification, so independents, Republicans, and Democrats, type of agency that they went to. So for example, if they were on the IRS website or Social Security website or the census. So I compare these models based on these dimensions. One thing that I found was there was no difference in terms of gender, race, education, and income. In other words, the service quality model works equally well across genders, works equally well across race, works equally well across educational levels and income levels. But I did find some differences in age, political identification, and type of agency experience. So let's actually see what those differences were. So these are the paths for 13-serve. I've graded them out, and I'm going to highlight those paths that I found different among the groups. So the first path that I found different when I looked at the age is the website quality and overall quality link. So Generation XY places a much more premium on website quality than baby boomers. So it seems to me that the website quality matters more for younger people than for older people. Now, this is what the data are telling me. At this point, I can start churning my theoretical wheels and say, why this might be happening. So I can start to conjecture at that point. Okay. It is possible that younger people have seen better websites. They have more sort of exposure to internet, and they're able to gauge the website quality much more better than baby boomers. And if the website is not of that good quality, their perception of overall quality kind of impacts. The other thing, and this is one of the more, I would say, politically charged thing that we found, and this is, the data are telling me, I didn't say anything. So I don't want to get into debate with that, but so what we found was that the website quality to trust link was different for independents, Democrats, and independents and Republicans. In other words, independents' perception of trust suffered more due to the website glitches than Republicans or Democrats. So when the Obamacare fiasco happened, it is possible that the ratings that Obama suffered, or the dip, was because of the perceptions of independence. Republicans and Democrats have already made up their mind. They either love him or hate him. And no matter what the website is doing, it doesn't matter for their levels of trust. Okay, so that was one thing that came out of the data. And this is something, again, I'm conjecturing. The other thing that we looked at was the type of agency that you experience. When you go in, you are looking at either, IRS websites or census or Social Security. One of the things that we found was that the information quality to the overall quality link was different for IRS and census and Social Security and census. Meaning if you are going on the IRS website and if you're looking for information, the quality of information impacts the perception of overall quality more than if you are on the census website. And the same thing for Social Security and census. Now, my I'm not from here. I haven't grown up in the United States. I came here 8 years ago. But my sense is that when you go on the census website, you're not looking for very critical pieces of information. In other words, you're allowing certain weaknesses or whatever in the data that you're getting. But when you're on the IRS website or in the Social Security website, the information quality suddenly becomes very, very critical. Not as much as when you're on the census website.
Probably because there's more of a financial tie to both those.
So that's what I'm getting at. If you're on the IRS website or on the Social Security website, you're dealing more with your financial stuff, financial data, but you're on the census, you're like, yeah, okay, I just have to reveal my race, gender, and income. And so that might be possibly what's going on there. So, conclusions for this study, for the e-government study, constructs in the expectancy disconfirmation theory are good at explaining variance and trust, but constructs in the service quality model are good at predicting trust. So now we've done this neat comparison, and if your job as a practitioner was to predict the level of trust of your respondents, you would go with the service quality model. Okay? The other thing that we found was that the service quality model is generalizable across gender, race, education, and income. However, we found some interesting differences in age, political identification, and type of service accessed. Okay. So not only have we figured out which model works out best for explanation or prediction, but we've also figured out the boundaries. And that's what you will do when you're doing studies for medical trials or whatever. If you're trying to build models which are going to predict if somebody's going to have a heart attack or not, you want to go with the model that predicts the best, irrespective of whether at the current stage you have the theory to explain it or not. Because you really want to predict heart attack rather than just do a good job at explaining and not predicting at all. So in that scenario, you would want to go with a model that does very good at prediction, but also you would want to look at for which subgroups that model does better and for which subgroups it doesn't do as well. So that might be something of a takeaway here. So the overall conclusions of this talk is that the explanatory and predictive modelings have different goals. Best explanatory models may not be best at prediction. PLS-SEM can be helpful there. The other advantage that PLS-SEM has over other techniques such as neural networks is that you can actually see the structure. If you're working with neural networks, a neural network hides a lot of detail. You won't see the arrows going in. All you see is a black box. You put in the variables and out comes the prediction. But if you're interested in theory building and if you're interested in looking at you're opening the hood and trying to see how that prediction is happening, then PLS-SEM is a really good technique because you can actually see which way the arrows are flowing. And I think that that's a very powerful thing to have in your toolkit. And so even though neural networks do a really good job, you're stuck in terms of building your theory ahead. But PLS can actually allow you to do that. So where can predictive modeling help? Prediction is a goal in scientific research. It's an established goal, and it's much more so for medical professionals such as yourself. You can generate new theories with it. Sometimes our theory lags behind. We have a lot more data these days, and we don't really have a lot of theories floating around to explore that data. Maybe there are certain theoretical paradigms just floating out there that we haven't really touched them yet. So when you start looking at the data, when you start looking at prediction can actually help you come up with newer theories that explanation cannot. You can compare competing theories, you can improve on existing models, and most importantly, prediction allows you to assess the relevance between theory and practice. For medical professionals, I guess this is one of the biggest takeaways because you don't really want to live in a theoretical world. You want to see your interventions, medical interventions work, and you want to know how good they work. Right? So that is where predictive modeling can be of real good help. So that was my talk, and that's my email address right there. If you have any questions.
That was an excellent presentation.
Thank you.
We have it recorded, right? Do you have like a bibliography of PLS that you could distribute?
Yes, I can actually. I was going to put some of the citations that I used in this slide, but I wasn't sure if I should do it in this slide. But I can definitely send her.
Yeah, you send it to Sarah Fagan.
Yeah.
So, this was fascinating, thank you so much. So what's the difference between PLS and the traditional predictive models that we do all the time, that Paul does all the time?
Yeah.
Is it because of the latent variables that can be only used in the PLS?
Yeah, so that is one of the major differences between, let's say, you can do predictive analytics with OLS, right? You can build predictive models with ordinary least squares. But many times you're working with latent variables. And if you're dealing with constructs such as, I don't know, a general health construct, that a general health construct would include a lot of indicators, right? It would include your weight, your heart rate, or whatever. If you're looking at that kind of construct, which is more of an abstract kind of, then PLS is very useful there. But if you're looking at just the observed variables, then you stick with regression. I hope this talk was useful. Thank you so much.